It's my great pleasure to introduce Jennifer Aminzade, who I worked with when she was a graduate student in the Department of Earth and Environmental Sciences at Columbia University. Jennifer's topic then, as it is now, is the projection of future drought associated with global warming. She became a true expert in this field, which one might say is of the greatest importance to mankind. You can't say that about every research topic. Jennifer, thank you so much for giving this webinar and helping people appreciate the potential issues concerning water availability in this warming planet. And nice to talk with you again, Jennifer.
Yeah, thank you, David. So should I go ahead with my talk now, or will there be an introduction for the other speaker as well?
You can go ahead with your talk now, and the other introduction will follow.
Okay, thank you. Here we go. I'll share the screen. Oh, I just need to wait till the Daniel, if you could stop sharing your screen.
Okay.
Okay. Okay.
In the meantime, it's very nice to hear your voice. It's Cynthia.
So it is so wonderful to hear both you and Cynthia, both you and David. This it's been way too long.
Come to New York and come visit.
I need to. But thank you for having me present today. It was an honor to work with David on my PhD research. And it's wonderful to be part of this lecture series and book celebrating his work. I think I can X out of this real quick. Here you go. So today I'm going to talk about projections of future drought, the importance of fresh water to our societies and ecosystems cannot be overstated. We have all seen the impacts of severe drought and flooding around the world, and speaking as a Californian, the idea of an increase in drought or flooding severity is very disturbing, to say the least. In the past, drought and flooding have been driven to a very large extent by too little or too much precipitation, respectively. However, in the 21st century, rising temperatures are likely to play a large part as well, not only through their impact on precipitation patterns, but also due to temperature's impact on evaporation. According to the Clausius-Clapeyron equation, every 1% increase in temperature increases the water holding capacity of the atmosphere by approximately 7%. As temperatures increase, the atmosphere is able to hold more water vapor. A global increase in atmospheric moisture demand is projected. Future droughts may occur primarily because of temperature increases and may even feature increased precipitation. This is why looking at projected changes in precipitation alone is not enough. There are many ways to define drought. My research focused on two types of water availability measures, soil moisture and drought index values. So in theory, soil moisture provides the most essential information needed for drought determination. However, there is a lack of long-term global root zone soil moisture measurements. In situ measurements are sparse and infrequently sampled. This has led the agricultural industry to rely heavily on drought indices that can be calculated from commonly available meteorological inputs such as temperature and precipitation. At the time of this research, satellite soil moisture data was limited to the moisture in the top centimeter of soil or vegetation, or it included all terrestrial water, including groundwater storage, neither of which gives us the needed root zone soil moisture. But it looks like global root zone soil moisture may now be available from NASA's SMAP satellite, but it was not available during the time of my research. The image you see here, these are the 1901 to 2100 global monthly soil moisture projections from 5 IPCC AR4 GCMs using the climate of the 20th century and the SRES A2 scenario for the 21st century. They show little change globally as the climate warms. Notice how different each model is. There is no standard among models on how soil moisture is defined. Each model has their own method. The soil and vegetation is divided into multiple layers of varying thicknesses with varying physical regulations, which make intermodel comparisons difficult. Although it's very hard to tell, all of these models are showing a slight decrease in soil moisture over time, with the exception of CCCMA. Since there is such a spread in soil moisture definitions between models, we tend to look at the percentage change from a control period or the change divided by the standard deviation. So here we see the percentage change from the 1979.
Looking for negative attention.
Oh. Was that a question?
Could everybody please, if you're listening in, mute your line, please?
So here we see the percentage change from the 1979 to 1989 average for soil moisture in the 5 GCMs. Now it is easier to compare and contrast the models. Only the GFDL model, which had the lowest control run value, shows strong decreases with time. I did compare these values with soil moisture from land surface models driven by weather station data between 1979 and 2010. I used the CLM, Mosaic, NOAA, and VIC models. I noticed two things. The LSMs show, land surface models show far more agreement than the GCMs, and the trends in the land surface model soil moisture show a global decrease that is much stronger than what we find in GCM output for the same period. So it is possible that the GCMs are underestimating decreases in soil moisture. In addition to soil moisture, I also looked at future drought using drought index calculations. There are many drought indices used today. I focused on 2, the Palmer Drought Severity Index, or PDSI, which is widely used in the United States, and the Supply Demand Drought Index, or SDDI, which is based on the difference between precipitation, which is the atmospheric supply of water, and potential evapotranspiration, the atmospheric demand for water. The SDDI was developed by David Rind. It has been shown to be highly correlated with PDSI in the United States. SDDI requires only monthly mean precipitation and temperature as inputs for each location without requiring regional coefficients required for the PDSI, which are not commonly available worldwide. The table here shows the classifications of flood and drought, which can be used for both PDSI and SDDI. The positive numbers are for wet conditions and negative numbers indicate dry conditions. So what trends do we see in SDDI over the next century? This slide shows the SDDI trends between 1901 and 2100 using simulated surface air temperature and precipitation from 5 models for 2 IPCC SRES scenarios. A2, which has strong population growth, self-reliance, and preservation of local identities, and A1B, which has rapid economic growth with a balance between fossil and non-fossil energy sources. We see a big change from 2000 to 2100. All models show strong increases in global drought conditions as the 21st century progresses. Increases in negative SDDI values indicating dry conditions can be due to either potential evapotranspiration becoming relatively larger than precipitation, or precipitation becoming relatively smaller than potential evapotranspiration. Since the global average of both precipitation and potential evapotranspiration are increasing due to increasing temperatures, the relative rates are of particular interest for future water availability. We can see here that the impact of the IPCC SRES A2 storyline choice for the 21st century is, in most cases, smaller than the differences between the GCMs.
Just sorry to interrupt, Jen, but you can close out of that window on your screen. There's a chat message. For folks on the...
Oh, it's actually not showing up for me.
Oh, no, don't worry about it then. It's on. Don't worry about it. Sorry about that. You can continue.
Okay, is there something I can do to make it go away if I...
It's on my screen that I'm using here to project in the room. That's why.
Oh, okay. Okay. So that's okay now. Okay. Here we have soil moisture and SDDI side by side. Soil moisture anomalies from their 1971 to 2000 averages are divided by the 1971 to 2000 standard deviation. The actual value of the SDDI is shown. It's calculated using modeled and observed surface air temperature and precipitation. Over the next 100 years, global average SDDI predictions over land steadily decrease, indicating severe drying globally by the year 2100 in all models. In contrast, global average soil moisture projections show almost no change in the 21st century in all models except the HAD-CM3 model, which shows a steady decrease. Okay, if we look at extreme drought and flood conditions in soil moisture projections, a new picture arises. These figures show soil moisture projections. These figures of soil moisture projections show the percentage of grid boxes in each model experiencing 5% drought or drier conditions in June, July, August, and December, January, February on the top row, as well as 5% flood or wetter conditions in June, July, August, and December, January, February on the bottom row. In the previous slide, it seemed as if soil moisture was hardly changing in the 21st century. However, by examining these extremes, we see that both severe drought and flooding are increasing with time. However, there are still differences among the models. In the previous slide, HAD-CM3 showed a globally average decrease in soil moisture because the extremely wet conditions do not occur as much as the extremely dry conditions in that model. Here's the same plots for SDDI. These figures use SDDI projections to show the percentage of grid boxes in each model experiencing 5% drought and 5% flood conditions or worse in June, July, August, and December, January, February. For the 5% drought, the soil moisture changes are less severe than those for SDDI, especially in summer, while the 5% flood condition increases are greater for soil moisture than for the SDDI in both seasons. For SDDI, extreme drought outweighs extreme fluvial conditions, although both show increases. This is why global average SDDI shows a strong drying trend. Here's a zonal average view of the projections. These are the June, July, August, and December, January, February zonal land-only SDDI and soil moisture percentage change differences between the end of the 21st century and the end of the 20th century. And note that the negative latitudes are in the southern hemisphere. In both summer and winter, changes from the 20th to 21st century show that SDDI experiences drier conditions in the tropics, ranging from mild to extreme. There is more agreement among the models that there are extreme decreases in in mid-latitudes. In the Arctic, the models show increased SDDI, indicating wetter conditions ranging from moderate to extreme. Soil moisture percentage changes show the equator getting slightly wetter over land, consistent with increased upwelling. There is drying in the north and south between 35 and 40 degrees latitude, and in some models between 10 and 30 degrees in the northern and southern hemispheres. The change in the lower latitude tropical portions of this region are due to changes in the mean circulation and precipitation over land. The subtropical changes seem to be more associated with warming temperatures and increased evaporation. The strong variability in GFDL is due to the total global soil moisture being an order of magnitude less than in the other models. So on this slide, we see the soil moisture mapped out. These figures show the December, January, February 1979 to 2010 mean soil moisture, and the June, July, August, and December, January, February seasonal anomalies for the end of the 21st century. Please note that the color bar scales for GFDL and Maroc are different from the others because of a large difference in values. Disagreements on soil moisture values between the GCMs are primarily due to differences in soil moisture depths, which lead to very different soil moisture magnitudes. Although the magnitudes of soil moisture in the various models disagree, there are some common patterns that emerge, such as GFDL, HADCM3, and Maroc, all showing patterns of high soil moisture at high northern latitudes. Also, all of the models have relatively high soil moisture over notoriously wet regions, such as the Amazon basin, and low soil moisture over the world's deserts. However, a brief examination of these figures shows that the differences in soil moisture between models tend to outweigh the similarities. June, July, August, and December, January, February soil moisture means show very little difference, indicating that soil moisture does not show large seasonal shifts in the models. Moving into the 21st century, soil moisture patterns show very different regional changes in each model. However, there are no obvious global or zonal patterns in the changes. Here are the same figures for SDDI calculated using temperature and precipitation input from our 5 models. There is much better agreement among the models for both the control runs and future seasonal values. June, July, August, and December, January, February SDDI means show a clear difference, indicating that SDDI has larger seasonal shifts than soil moisture in the models. Moving into the 21st century, SDDI patterns look dramatically more dry than the 20th century for all 5 GCMs. According to PDSI classifications, most land surface in the last 30 years of the 21st century is in at least moderate drought conditions. Now we have a good idea of the long-term mean state of soil moisture and SDDI in the 20th and 21st century model runs. As you can see, there is very little agreement between the 2 water availability measures. The discrepancies between soil moisture and SDDI are largely related to differences in the way that evaporation is calculated. So let's take a step back and look at the modeled meteorological changes driving the changes we see in 21st century soil moisture and SDDI projections. Here we have the global changes in land surface air temperature, cloud cover, precipitation, and precipitation over land. We see a great deal of agreement on land surface air temperatures between models. For precipitation and cloud cover, there is much more variability. Over land, some models show steady increases in precipitation over the 21st century, and others exhibit only minor increases. Globally, the 5 models show increased precipitation ranging from 1.5 to 6 millimeters per day by the year 2100 over land. Precipitation and temperature changes also have a fairly strong agreement among the models and in the 21st century. However, changes in temperature and precipitation compete against one another in their influence on water availability measures. Which of these factors has the most influence on SDDI and soil moisture calculations? This series of maps shows the time series correlation between soil moisture and surface air temperature on the top row, between SDDI and surface air temperature on the second, between soil moisture and precipitation on the third, and between SDDI and precipitation on the bottom row. We see the influence of precipitation on SDDI and soil moisture is fairly similar. However, the influence of temperature is most pronounced for SDDI. SDDI, through its evaporation term, reacts more strongly to temperature than does soil moisture. So, an essential component of drought index and modeled evapotranspiration calculations is the potential evapotranspiration. Evapotranspiration describes the amount of moisture moved from the land to the atmosphere through evaporation and vegetative transpiration. Potential evapotranspiration is the evapotranspiration from a thoroughly wet surface. Over a wet surface, such as a lake or ocean, evapotranspiration should roughly equal the potential evapotranspiration. There are many methods for calculating potential evapotranspiration that are commonly used today. 4 are shown here. This is a 1901 to 2100 timeline of potential evapotranspiration using 4 different calculation methods: aerodynamic, Thornthwaite, Hargreaves, and Penman, using inputs from the GIST-GCM. All 4 of these potential evapotranspiration calculations are increasing in the 21st century. Aerodynamic potential evapotranspiration stands out as being an order of magnitude larger than any of the other potential evapotranspiration values and having the largest seasonal variability. Evaporation in GCMs, the source for the modeled soil moisture values for all 5 models we've been discussing, is determined by multiplying the aerodynamic potential evapotranspiration by a scaling factor that will be referred to as beta. Beta ranges from 0 in very dry conditions to 1 in well-watered conditions. The aerodynamic method for calculating potential evapotranspiration assumes that the surface-specific humidity is at the saturation value. This causes an overestimation because the surface temperature would actually be lower if the ground were saturated. So aerodynamic potential evapotranspiration values are very high. For this reason, the beta factor must be small in GCMs, which means the 2 variables used to calculate it, atmospheric and surface conductance, must also conform. The atmospheric conductance must always be larger than the surface conductance, although that's not always the case in the real world. The Thornthwaite method is the default method used to calculate SDDI and PDSI. Thornthwaite is based on an empirical relationship between potential evapotranspiration and surface air temperature. In the SDDI formulation, the evaporation represents the atmospheric demand for moisture and is therefore set to a maximum value, the potential evapotranspiration. If there were a beta term in the SDDI, it would always be 0. And we'll revisit beta in a moment. Next, we see the impact of these 4 very different potential evapotranspiration methods on SDDI. Here's the June, July, August mean 2081 to 2100 SDDI calculated using the same 4 potential evapotranspiration methods: aerodynamic, Thornthwaite, Hargreaves, and Penman. The most severe SDDI projections are for the SDDI calculated using the aerodynamic potential evapotranspiration. The Hargreaves SDDI is the least severe by 2100. We see that the potential evapotranspiration method with the largest change over time has the largest impact on SDDI. The maps show that there are many regions of agreement, like Northern South America, Northern Africa, and Southern Europe, even though the potential evapotranspiration methods are very different. Areas of agreement are likely regions in which temperature dominates the potential evapotranspiration calculation, since temperature is the common factor for all of the methods, directly for Thornthwaite and Hargreaves, and indirectly through the saturation vapor pressure equation for aerodynamic and Penman. Regions of disagreement are most likely areas where a variable other than temperature has a larger influence on the calculation, such as specific humidity or shortwave radiation. To dig a little deeper into the differences of SDDI and soil moisture, we decided to take a closer look at evaporation and the beta term I mentioned a moment ago. In the GISS model, the evaporation is calculated from the aerodynamic potential evapotranspiration with an efficiency factor beta for scaling. Beta equals the surface conductance, either bare soil or canopy, divided by the sum of the surface canopy conductance and the atmospheric conductance. The evaporation is then calculated using the formula evaporation equals beta times the aerodynamic potential evapotranspiration. Beta is maximum in well-watered conditions and minimum when the soil or vegetation is driest. So for soil moisture, beta continuously changes with time. For SDDI, there is no beta. If there were one, it would always be 1 because in its formulation, evaporation represents the atmospheric demand for moisture and is therefore set to a maximum value. For PDSI, beta has 12 monthly fixed values that stay constant from year to year. So what if we alter SDDI and add a fixed beta term like the PDSI has, and add a dynamic beta like the models use? If we add SDDI with fixed beta, we see that it lies in between the original SDDI and soil moisture. If we add the SDDI with dynamic beta, we can see that over time, SDDI with dynamic beta is closer to soil moisture than the original SDDI. So by reducing the evaporation in the SDDI to below potential values via beta in the upper right, and also by allowing beta to change in the lower right, SDDI projections are brought closer to the GCM soil moisture changes in the lower left. Here we have a 1981 to 2000 timeline comparison of SDDI standard and with fixed beta and dynamic beta, as well as PDSI and soil moisture. The SDDI and PDSI were calculated with actual temperature and precipitation data. We also have modeled soil moisture values. Adding fixed and dynamic beta does indeed move SDDI toward soil moisture, but it also drives SDDI away from what PDSI says is true for the 20th century. PDSI has not only been used for the 20th century, it has some additional credibility since it has been used to reconstruct paleoclimate water availability from tree ring variations and is commonly used by the National Weather Service to depict current drought conditions. If soil moisture and SDDI with dynamic beta are accepted as the more reliable measures of future water availability, a variable that is often overlooked in the land surface scheme, beta, is being trusted. So how well is beta understood? There are many factors that will influence beta over the next century that are not well understood today. With warmer temperatures, there will be regional shifts in vegetation as well as changes in plant physiology. There is an additional category of uncertainties, perhaps more difficult to predict. Humans can easily cause changes in beta. Changes in land use patterns as well as growing and shifting populations can all influence beta. Beta is calculated with surface and atmospheric conductance. As discussed previously, there is reason to suspect that the surface and atmospheric conductance values are not representative of real-world values because of the need for a small beta to balance the large aerodynamic values. Given the significance of beta in this study, we were curious to take a closer look at beta's components, canopy conductance and atmospheric conductance. So for beta to be small, the canopy conductance values are always much smaller than atmospheric conductance, which creates a situation where vegetation always limits evapotranspiration. The GISS model was run with canopy conductance multiplied by 3 to better match observed values. The 3 times canopy conductance run displays a strong decrease in summertime surface air temperatures over land and a small decrease in surface air temperature over land in the winter. Temperatures decrease due to increased evapotranspiration causing cooling at the surface. Precipitation increases over land in the summer, most likely because of the increased atmospheric water from evapotranspiration increases. We found a disagreement in the soil moisture and SDDI responses. There is increased drying in soil moisture in the 3 times canopy conductance run because of the increased surface conductance and resulting evaporation. While SDDI shows wetter conditions due to decreased temperatures and increased precipitation. The change in surface conductance by creating milder SDDI projections and more severe soil moisture projections shows another way it's possible to bring the 2 water availability measures closer together. So, in conclusion, SDDI and soil moisture are 2 very different ways to evaluate future water availability. They are calculated in different ways. However, they both project a significant increase in extreme drought and flooding in the 21st century. SDDI drought projections are more severe with increased drought conditions from the tropics through the mid-latitudes. Soil moisture projections show increased drought primarily in the subtropics. By limiting the evaporative response through beta and the drought indices and increasing the canopy conductance in the models, we're able to bring the projections of these 2 water availability measures closer together. Now that we know the reasons these 2 measures are different and we know how to alter SDDI to make it more similar to soil moisture, we have to get back to the question of which one is better. I think the most important thing to ask is what would make one of them be a better choice than the other in a warming climate. We expect to see shorter duration, more intense storms according to IPCC. Soil moisture could handle this, but this change, but SDDI could not since it uses average monthly precipitation. We expect that average temperatures will continue to increase. Both measures can handle this change. And we expect to see regional shifts in vegetation and changes in stomatal conductance due to increased CO2. GCM vegetation schemes are working to handle these changes, but the SDDI is blind to vegetation. So on the one hand, we have a complex land surface scheme, and on the other hand, a simple formula. Since neither measure is perfect, complex and simple both have different pros and cons. It is important to understand the abilities of each, and since they have different strengths and weaknesses, perhaps the best approach is actually to use both, and when they disagree, we can decide which is most appropriate to the situation, and when they agree, the strongest case can be made for a model's water availability projections. So that is all, and thank you. I'd be happy to take any comments or questions.
Thank you so much, Jen. Anybody on the line, if they have a question, you can either send it to me in the chat window, Dan Bader, and I will be able to read it and we can have it answered. And I think, David, do you have any questions as well? So maybe we'll start with you.
Hi, Jen. Thanks for that great presentation. You're living in California now.
Yes.
What is your impression about droughts in California? Are they primarily associated with temperature changes, precipitation changes? Do those correlate so well that you can't differentiate them?
I mean, yeah, it's, well, it has been, it has definitely been defined by a lack of precipitation, it seems, but the temperatures have exacerbated it. I can definitely see a change in climate. I lived in California in this area before I came to New York for grad school, and then I moved back here, and there are a lot of changes even in the last 10 years that we're noticing, and a lot of stories of people who've lived here their whole lives and are older now telling us how different things are today than they used to be so in 50 years ago. But so I don't know, I think everything I know about California drought at the moment is anecdotal and word of mouth type, but it does feel like in general all of the things that I was learning about in grad school in my classes, these things are starting to happen around me, and I definitely feel like California is feeling it.
Just one quick follow-up. Do you know what the projections are? Are there coherent projections for what will happen to California in the future?
I think I would have to ask you. I actually don't, I'm not sure, David. I'm not sure. I haven't, I'm not up to date on what's happening currently other than just as a citizen, but not as a scientist.
Yeah, one factor that does seem to enter in, of course, are the ENSO cycles.
Yes, of course.
And my understanding is that one of the things that's contributed to the more recent droughts have been the relative negative phases of the ENSO cycles, with more La Niñas than El Niños. Richard Seeger at Lamont, for example, has made the case that he thinks that has influenced California drought, or drought in the Southwest, more than climate warming per se. But we don't know what's going to happen in the future. Models seem to project more El Nino events, but people have pretty much zero confidence that that projection can be relied on. So that's just an additional factor, at least for California.
Mm-hmm. And something really interesting to me, coming from this drought background, is seeing what happened when we had years of drought in California, followed by an incredibly wet winter, where all this vegetation grew up, and then you add another like dry season after that, and then all these forest fires, all these wildfires that had so much kindling from that new growth after the really wet year. That's something that was really fascinating to me and very scary. It's something I didn't get into with my thesis, but it could have easily been another branch to look into. The wildfires have extremely affected California.
Thank you.
So we do have one question from one of the participants. The question, it says, it seems we're in unprecedented times. What has surprised you the most about what you've learned, and how worried should we be right now?
So I guess I did this research between 2005 and 2011. So I've seen these projections for a long time now. So I guess it feels like something I've known forever, and it's hard to go back to. So I think we should be concerned and do what we can to head off, if we can get off this path that we're on. But I think we also have a lot of amazing people in this world that if we put our heads together, we can work on this problem and hopefully head it off and keep us from getting to the point that we're seeing in some of these slides in the year 2100.